today's speaker. He is Professor Stuart Parkin from Max Planck Institute of Microstructure Physics in Halle, Saale, Germany. And our today's Kharkiv Quantum Seminar is co-organized with German-Ukrainian Core of Excellence named Plasma Spin Energy. The title of today's talk is Spintronics for Massive Data Memory Storage, Past, Present, and Future. And I would like to introduce to the audience our today's speaker. Stuart Parkin is director at the Max Planck Institute of Microstructure Physics and an Alexander von Humboldt professor at the Martin Luther University Halle-Wittenberg. His research interests include spintronic materials and devices for advanced sensor, memory, and logic applications, oxide thin film heterostructures, topological metals, exotic superconductors, and cognitive devices. Parkin's discoveries in spintronics enabled a more than 10,000-fold increase in the storage capacity of magnetic disk drives. Stuart Parkin received his PhD in 1980 from the University of Cambridge. Professor Parkin is a Fellow of Royal Society, National Academy of Engineering, German National Academy of Science, Royal Society of Edinburgh, Indian Academy of Sciences, and Academy of Sciences for the Developing World. Professor Parkin's awards include Europhysics Prize for Outstanding Achievement in Solid-State Physics, Alexander von Humboldt Professorship, Millennium Technology Award, ERC Advanced Grant Super Mint, and APS Medal for Exceptional Achievement in Research. He has published more than 700 papers, has more than 128 issued patents, and has given impressively more than 1,000 invited talks all around the world. Parkin was named a highly cited researcher for the last several years. So with this, with great pleasure, I would like to pass the microphone to Professor Parkin. Please, Stuart.
Okay, thank you very much. So if you let me share my screen, I'd be happy to show you my foils. Okay, so they've done that. I share my screen. Share. Oh, that one, this one, that one. Okay, well, thank you very much for the invitation to give this talk. And today I'd like to tell you something about the general area of research called spintronics and how this has led to three important technologies for storing digital data. So I want to talk a little bit, if you like, about the past, the present, and the future. In the video here, you can see some of the laboratories that we built since I moved to Max Planck. I was appointed a director here in Germany in 2015, but it took 3 or 4 years before we could renovate these laboratories. So we really started in 2018. And in particular, our main interests lie in developing or creating new materials, one atomic layer at a time, using various techniques for depositing these materials, using magnetron and ion beam sputtering, using molecular beam epitaxy, or using pulsed laser deposition. And then these films, we basically build devices from them using advanced electron beam and optical lithography, and we measure their properties using a wide range of magnetic transport and optical techniques at temperatures ranging from 40 millikelvin to high temperatures. Now, I'd also like to mention then that very fortunately, we last year were awarded this funding from the BMBF in Germany, and to support a core of excellence between ourselves and the Kharkiv National University and the National Science Center in Ukraine. We're very pleased that we could receive this funding, and this funding relates strongly to my own research interests in spintronics, and in particular in plasma science. How can we build better ways of developing concepts for depositing materials, for example? And this means we need to build new types of devices for exploring the plasma physics to enable better types of plasma-based technologies, in particular for depositing thin films to create these atomically engineered materials, but also to create devices using these new plasma techniques. And I'm very pleased that this was funded for the next several years with 2.5 million euros of funding. Initially, the center will be based here in my institute, but we hope that eventually we can transfer this center and the people in the center back to Ukraine. And initially, we would have experimentalists based here in Germany, but theorists and theoretical work can be carried out currently in Ukraine just through the use of computing systems here and at the Max Planck Society, for example. And as you can see from this cartoon, we want to basically create plasmas with very well controlled energies and of particles that will enable us to build better devices. So I would like to acknowledge Andriy Shchevoyedov here in my department at the Max Planck Institute, who helped to motivate this funding opportunity and who's here on the call, who can answer any questions related to this collaboration. And I'm very happy that Alexei Cheshchin from Potsdam University agreed to become the head of this Center of Excellence for the next 4 years. So I'm happy to answer any questions about this, but I'm very pleased that we have a means of collaborating with scientists in Ukraine on this important topic. So if I just give you, I'm going to give you a very general introduction, and then of course our interest here, unlike most Max Planck institutes, which are normally fundamentally related to basic fundamental physics and chemistry and biology, our interests really are exploring materials with novel properties that can allow for new devices to store and to compute with digital data. And over the last 100 years, the means of computing has evolved from mechanical means to vacuum tubes to discrete transistors to the last 40 years of integrated circuits. And however, these integrated circuits, basically the CMOS technologies of today, have come to the end of their technological roadmap, and we need to do something else. And so we ourselves and others are very interested in, for example, quantum computing. Instead of having binary bits, which are zeros and ones, you can have bits that have a phase that can vary over a wide range. And this enables one device to compute more effectively. However, quantum computing, as you know, it's really today about error correction and about building networks of devices at the large scale. This is very challenging. And at the same time, there's another area of computing, which is called cognitive or neuromorphic computing, where we imagine new types of devices and networks of devices that can compute as energy efficiently as our own brains. And our brain consumes about 20 watts, and generally it's agreed that to build a computer today with comparable computing power using CMOS technologies would take 100,000 times as much computing power, something like this. So these are very interesting areas of research, and how can we achieve them? We need to go beyond devices that use the electron's charge to, for example, and this is my talk, it's about using the electron spin. We and others are also very interested in using currents of ions to manipulate material. For example, we can use ionic currents to change insulators to metals, metals to insulators. And this is something we're also working on, but I'm not going to talk about. And then finally, I think another very, very important evolution is evolving from two-dimensional technologies as of today. CMOS technology is innately two-dimensional to moving to innately three-dimensional technologies. And this is something that we and others are working on, but it's very challenging. So these are very, very interesting challenges involving a lot of fundamental new science and technology to go beyond the computing systems of today. So now I want to take you back 550 years. And at that time, a very important technological revolution took place. A scientist in Germany, in Mainz, the city of Mainz, Johannes Gutenberg, invented the movable type print. Basically, he could print books. And this essentially meant that he could print what is analog information. And because prior to his inventions, instead of printing multiple copies of book, you had to basically use a pen and a piece of paper. So that meant it was very expensive and knowledge was confined to small numbers of people. With the advent of printing, knowledge could be widespread. And this led, if you like, to the next 500 years age of the use of knowledge, the knowledge-based eras of today. So now, about 70 years ago, the end of the Gutenberg technological evolution took place when IBM in California, in San Jose, where I worked for 30 years, invented a technology called magnetic disk drives. And in a magnetic disk drive, as shown in this cartoon, this is a modern age disk drive, a small disk. Today it's roughly 3 inches or so in diameter, 3.5 inches in diameter. Is rotated, and a device, a reading head or recording head, reads the information and writes the information in the surface of a very thin magnetic film deposited on a disk, which is typically made of glass. And this disk is rotated at high speeds, 10,000 revolutions per minute, and enables the storage of maybe 2 or 3 terabytes of information in a device containing one or more disks. Now, over the last 70 years, the storage capacity of these devices has increased maybe 1 billion times by shrinking the size of the magnetic region in which the information is encoded. And so on the bottom left, you can see a magnetic force microscopy image of small magnetic regions. You can see the white and black correspond to the north and south magnetic poles as these regions are shrunk to smaller dimensions. And as I said, these regions today are of the order of 20 nanometers in extent and are about 1 billion times in area smaller than was possible 70 years ago. And so the cloud today, it's all about computing, but really in the cloud, you will see stacks and stacks of magnetic disk drives. And this essentially is the basis of the most important and the most valuable corporations today. These corporations are based on access to and use of data stored in magnetic disk drives. 70% of all digital data today is still stored in these magnetic disk drives. And this is just shows you then, this is a very nice paper. It's more than 10 years old, but basically, in roughly speaking, roughly 20 years ago, we moved from the era of analog computing, where information was encoded in books and newsprint, to the modern world in which information is largely encoded in digital bits, mostly in hard disk drives. We move from books to disk drives. No longer need to go to the library to access essentially all the books in the world, all the information in the world is at our fingertips. And the reason for this is because of spintronics. So I want to briefly discuss this. So what is spintronics? It's simply the notion that an electron, of course, has a charge. It also has a spin, a quantum mechanical property. The spin points up or down, and we can manipulate electronic currents. So the electronic currents have a spin in one direction or another. And in magnetic heterostructures, thin film structures, we can control the flow of this spin polarized current. So let me give you an example. And this is something that I invented when I was at IBM many years ago. It's called a spin valve. So if you take a metallic conductor like copper, shown as yellow, and you introduce current from a battery on the left-hand side, then of course the current will be carried equally by spin up and spin down electrons, shown as these red and blue objects. And they will be scattered after some distance, which is the mean free path of the electrons. So now we take a material shown in blue, which is magnetic. And when you introduce current from a battery, initially the current will be, again, consisting of electrons, equal numbers of red and blue. But because these are scattered, the scattering rates for the spin up and spin down electrons in a magnetic material is distinct. And this means that after some short distance, the current will be carried by electrons of one spin type more than the other spin type. This concept was actually proposed by an English, very famous condensed matter physicist, Neville Mott, from my university in Cambridge, where I did my PhD and undergraduate work. And he proposed this in the 1930s. That the idea is, in a magnetic material, the electronic current is innately spin polarized. So now we can take advantage of this if we have a sandwich of two magnetic layers, shown here as blue and red. One layer is magnetized to the right, that's a blue layer. One layer is magnetized to the left, that's a red layer. And these two magnetic layers are separated by a very thin layer of copper, let's say, a non-magnetic layer. So now when you introduce current from the left-hand side, the current in the blue layer will be carried by the blue electrons, and in the red layer by the red electrons. But because this copper layer is so thin, then the electrons, of course, are not traveling in the distance of the current, they're traveling in all directions. So the red electrons will cross the copper layer and be scattered in the blue layer and vice versa. So in this type of structure, all the electrons will be scattered somewhere. And therefore, the resistance will be higher than in the same structure where the two magnetic layers have their moments parallel. In this case, it's like a short circuit. The blue electrons can travel without a lot of scattering, and so the resistivity is reduced. And this we call the spin valve. In other words, by controlling the orientation of these two magnetic layers in this sandwich, if the copper layer is sufficiently thin compared to the mean free path or the scattering length of the electrons, then you can change the resistance. Now, it turns out then we proposed, we could use this as a magnetic field sensor, a spin valve magnetic field sensor to detect external magnetic fields. External fields will change the orientation of these magnetic layers and change the resistance of the device. So that's the spin valve magnet resistance. So now what happened was, well, it took us, so when I did the work that led to the spin valve in 1989 to 1991, it actually took IBM that had this disk drive company a few miles from the research center where I did this work. They could introduce this spin valve sensor as a means of reading information in a magnetic disk drive, as shown here. And this enabled rapid increase in the storage capacity of magnetic disk drives. And within a few years, the storage capacity was increased 1,000 times. So this led then to the magnetic disk drives being able to store all information in the world. And roughly speaking, a few years after we introduced this spin valve device, then a year's supply of magnetic disk drives could store all the information in the world. And this has led to an explosion of digital data. And as I said, then the development of companies whose business model is based on having access to vast amounts of digital data. And largely speaking, it's because of the spin valve device that enabled in the last 20 years, 1,000-fold or 10,000-fold increase in the storage capacity of these devices. Now, interestingly, just like CMOS technologies, these magnetic disk drives are coming to the end of their technological roadmap. And we need to find other means of storing data that can store more data. I want to talk to you then about two possible ideas. One is another proposal we made that we could build a memory, magnetic memory, using not a spin valve concept, but a magnetic tunneling device. The structure is the same as a spin valve. Two magnetic layers, separated not by a copper layer, but separated by an even thinner layer formed from an insulator, shown here as gray. And then the concept is, this is some work of myself, and also Jagadish Mudera at MIT was one of the first to demonstrate the possibility at room temperature that you could achieve a change in resistance of tunneling between two magnetic layers, shown here as red, through the gray layer, which is a very, very thin insulating layer. And the tunneling probability depends on the availability of spin polarized states. So in a ferromagnet, when you extract current from the surface, the current is automatically spin polarized according to the density of states of spin up and spin down electrons. And when they cross a tunneling barrier, these tunneling electrons have to find empty states with the same spin polarization. So when you have two magnetic layers that are parallel, then there are lots of empty states with the same spin polarization. Therefore, the tunneling current is high. But when you switch the magnetization, as shown at the bottom, so the two magnetic layers now have opposite magnetizations, then the tunneling current is significantly reduced. And what we showed in 2004, I showed that using a certain type of tunneling barrier, magnesium oxide, combined with a body-centered cubic cobalt ion electrodes, they have a very special characteristic that the spin up and spin down electronic states at the Fermi energy have very different electronic characters. The majority spin polarized electrons have extended sp-like states, and the minority electrons are more d-like. And this means that the sp electrons are spin filtered by the tunneling barrier, leading to effectively a near 100% polarization of the electrons via spin filtering through a non-magnetic tunnel barrier. And this leads to giant tunneling magnetoresistance values at room temperature. We demonstrated in 2004, actually in 2002, of several 100%. What Jagadish Mudera showed earlier was that he saw a few percent change in tunneling magnetoresistance at room temperature using amorphous aluminum oxide. But those are very tiny effects. So this enormous increase in tunneling magnetoresistance that we demonstrated in 2004, and there are even larger values today, makes it possible to use tunneling magnetoresistant devices not only for sensing data in magnetic disk drives, which happened in the mid-2000s, but also for another type of device, a magnetic memory device, where you store information in the direction of the magnetization of one of the layers in a magnetic tunneling junction. And so this means that Spintronics then has had two successes. One is using today magnetic tunneling junctions in the form of spin valves to read information in magnetic disk drives to sense tiny magnetic fields. And on the other hand, as we actually proposed in 1995, when I was at IBM, you could use a magnetic tunneling junction to form a non-volatile magnetic memory. The information is encoded in the direction of magnetization of one of the magnetic electrodes in a magnetic tunneling junction. And you could read the state simply by passing a tiny current through this tunnel junction to detect whether the tunneling current is high or low, corresponding to the orientation of this magnetic electrode. So it turns out later on, we originally proposed we would use magnetic fields to switch or set the state to write the information. Later on, it was shown that you could use the same current passing through the device, which is spin polarized, to deliver spin angular momentum. And that can be used to apply torques and therefore switch the magnetic state of the device from one state to the other. And today, this is the concept. Spin transfer torques are used to write, and the tunneling resistance is used to read. And this concept of a magnetic random access memory that we proposed in 1995 came to fruition in approximately 2019. So this is the idea we proposed in 1995. We demonstrated the first magnetic random access device in a few years later, in 1999. We already had exceeded 40% tunneling magnetoresistance. And then in 2005, with colleagues of mine at IBM Yorktown Heights, we demonstrated the first 16 megabit MRAM demonstrator chip fully functioning. And this was the first fully functioning magnetic random access memory chip that was competitive using conventional CMOS to build all the wiring circuits. Nevertheless, it took another 10, 15 years before magnetic random access memory became widely available since 2019, so only 6 years ago, and it has already largely replaced embedded dynamic random access memory. This spin transfer torque MRAM is as fast, but actually has a smaller form factor, and it's also replacing many other devices, microcontrollers, mobile cache, etc., because it is a non-volatile memory, unlike, of course, DRAM, which is a capacitive charge-based memory with leakage. This is the second major success of Spintronics. And this magnetic random access memory today is a business that's worth several $billion per year. Now I want to point out this is an innately two-dimensional technology. If you look in this cross-sectional view shown in the middle, then this shows you a magnetic tunneling junctions connected, a single layer of magnetic tunneling junctions connected to transistors, a two-dimensional layer of transistors in the surface of a silicon wafer, just like all CMOS technologies. Now, I want to briefly then summarize. Okay, so the spin valve head, which is based on magnetic multilayers, which are essentially atomically engineered, it relies on interface spin-dependent scattering, as I demonstrated in this time period. It became mass-produced just a few years later. This was extremely fast. The metallic spin valves were then replaced by magnetic tunneling junctions 10 years later. And nevertheless, this is the basis of vast increases in the storage capacity of HDDs, hard disk drives. However, that technology, as I mentioned, is coming to the end of its roadmap. On the other hand, magnetic random access memory, you see, has taken a lot longer. 1995, we first proposed this, not using metallic spin valves. We already proposed they would not be useful for applications in memories. You needed a high resistance device with vertical current passing through the device, which is a magnetic tunneling junction. And even though we demonstrated large scale devices in 2005, it took another 15 years for widespread application of this technology. Nevertheless, now it seems to be a rapidly evolving and important technology in CMOS foundries. Now I want to talk about another memory technology that I proposed, and I called it racetrack memory. This is the concept. As I already mentioned, you pass current into a magnetic material. The current is automatically spin polarized. A spin polarized current carries spin angular momentum. And so what we proposed was, well, if you passed a current which is spin polarized across a magnetic domain wall, as shown in this cartoon, then that current can deliver spin angular momentum to the domain wall and cause the wall to move. And this is the very simple concept. And this is what I proposed, that if we had a series of domain walls, as shown in the next foil, we could move all of those domain walls in the same direction by passing current into this racetrack. And the racetrack essentially is a uniform magnetic film. Now, today it's a complicated heterostructure. Nevertheless, the concept in this cartoon, you can see blue and red regions corresponding to magnetic regions magnetized in one direction and the opposite direction. And the boundaries between them, the magnetic domain walls, are what move in the presence of current pulses. These current become spin polarized just by scattering and can deliver spin angular momentum. And then I proposed this actually in around about 2002. And the concept was that if you build circuits using conventional charge-based electronics, CMOS, in a silicon wafer, you build a vertical racetrack which could contain 100 domain walls, and then you move the domain walls, the stored information in the form of the presence or absence of a domain wall by current pulses. You can move the domain walls, the elements, the memory elements, to a reading and writing devices built into the racetrack. And in this way, we could build in a small area of a silicon wafer, we could store 100 domain walls, increase the memory capacity by 100 times, and this would enable us to build in a solid-state memory chip, a device with the capacity of a magnetic hard disk drive. So hard disk drives are innately unreliable because you have a mechanical disk rotating under a moving head. And as mechanical objects, they can sometimes crash. This kind of racetrack memory would be solid state and would therefore be reliable, but it turns out it will be 1,000,000 times faster to access the first bit of information than a magnetic disk drive. So this, it seems, a very exciting possibility, and we've explored this for the last 20 years. And I want to just remind you some basic physics. So today, originally when I proposed this, we proposed moving the domain walls through something called this spin transfer torque. Simply current in a magnetic material is spin polarized, delivers spin angular momentum, moves the domain walls. Subsequently, it was discovered by ourselves and others. There's another very interesting way of driving a domain wall, which is something called a spin orbit torque. In this case, the spin angular momentum currents or spin currents, spin polarized currents, are derived in layers like platinum or tungsten. And these heavy metal layers display something called the spin Hall effect, which means that a charge current passing through a heavy metal layer will be subject to spin orbit effects, whereby the electrons with spins up and spin down will be scattered differently to the left and to the right. And this means it looks like a Hall voltage, but it's completely spin polarized. And so it means on each surface you would generate on one surface spins pointing up, and on the opposite surface spins pointing down. And on one surface then the spin current you generate can diffuse into a neighboring magnetic layer and give rise to a torque through the spin angular momentum. So this is the concept. If you take just a simple metal with strong spin-orbit coupling, then the charge current is turned into a transverse spin current, which is polarized in a direction perpendicular to that transverse direction and to the current direction. And then that spin polarized current can enable torques to be applied to neighboring magnetic layers into which the spin current diffuses. That's the idea of the spin orbit torque. And it turns out that it's more effective than the spin transfer torques by factors of up to a factor of 10, let's say. And on the other hand, we can detect the magnetic information in a racetrack either by incorporating a magnetic tunneling junction, where the racetrack layer itself will be one of the magnetic electrodes in the tunneling junction, and then whether the racetrack, as shown in this cartoon at the top right, points up or down compared to a fixed magnetic layer in the magnetic tunneling junction, this can lead then to a signal. We can detect the magnetic domains. Alternatively, we could use something called the anomalous Hall effect. It's not a spin Hall effect, but an anomalous Hall effect, which is within the magnetic layer itself, a charge current through spin-dependent scattering. Electrons with spin up and spin down are scattered with different probabilities to the left and to the right, and this leads to a transverse voltage like a Hall voltage, but the Hall voltage here is spin polarized. And this spin polarized Hall voltage can be used to detect the magnetization, whether pointing up or down. The sign of this anomalous Hall voltage will change when the magnetization is switched from up to down. So now, I wanted to mention then over the last 20 years, racetrack memory has evolved, if you like, in 4 major stages. Originally, this is racetrack memory 1.0. Then we proposed we would build a simple racetrack formed from an in-plane magnetized soft material like nickel iron or nickel iron cobalt. And the magnetic walls, these are vortex or transverse walls, can be moved by passing current through the magnetic material through this spin transfer torque. Okay, so in the case of soft magnetic materials, the domain walls are very, very wide because the domain wall width is related to the strength of the magnetic anisotropy and the magnetization. So if the anisotropy is very weak, then the domain walls would be very, very broad to minimize the exchange energy. So alternatively, you could make a form of racetrack from a perpendicularly magnetized material. This is racetrack memory 2.0, where now the domain walls are made much narrower by introducing a perpendicular magnetic anisotropy, typically by forming the racetrack magnetic material from alternating layers of distinct materials, e.g. cobalt and nickel. When these are atomically thin, the interfaces break symmetry and give rise to large perpendicular magnetic anisotropies. This was extensively studied in the 1990s. So this shrinks the domain wall by width by 100 times. So in racetrack 2.0, in cobalt, nickel, cobalt multilayers, we demonstrated we can move domain walls essentially in the same manner as in the soft magnetic materials. And they, roughly speaking, move at roughly the same velocity, about 100 meters per second, in the same direction, the direction of the flow of spin angular momentum derived from scattering within the magnetic materials. Racetrack 3.0 uses this spin orbit torques by generating spin currents in neighboring high spin orbit coupling layers such as platinum. And now these domain walls move actually in the opposite direction for platinum because of the sign of the spin Hall angle. And they move nevertheless roughly 3 times faster, maybe 300 meters per second. And then in 2015, we demonstrated actually the most important development was that we could build a racetrack that itself has no net magnetization. So in this cartoon, in racetrack versions 1.0, 2.0, 3.0, these are ferromagnetic films, and these ferromagnetic films have domains, and the domains have magnetic poles, and these produce long-range magnetic dipole fields, as shown in the cartoons. And these fields cause interactions within one racetrack and between racetracks, which means it's very difficult to build dense racetrack memories. So what we demonstrated in this version 4.0 was essentially we built one racetrack on top of another one, where by design, the upper racetrack would have exactly the opposite magnetization to the lower racetrack. So in this cartoon, if you look closely, you can see wherever we have a red region in the upper racetrack, it's blue in the lower racetrack. It means the magnetizations are pointing in opposite directions. And so by design, we could design these two upper and lower racetracks to have opposite and equal magnetization. So now there's no net magnetic flux. We've eliminated all the dipole fields. And it turns out at the same time, we discovered that in this kind of racetrack, because of the magnetic coupling, the anti-ferromagnetic coupling between the upper and lower racetracks, which we introduced by a very thin anti-ferromagnetic coupling layer formed from, in our case, ruthenium, a few angstroms thick, then we discovered that these domain walls, when you pass current through this device, move several times faster than in the racetrack 3.0. So now we can make these domain walls move at speeds of more than 1 kilometer per second, making this a very, very interesting high performance technology. So you see, in the space of 15 years, we were able to discover new physics and new materials that could enable the domain walls to be moved by current 10 times more efficiently than when we first started this project, or even more today. This is very exciting development of basic physics that makes this concept of a racetrack memory even more exciting today. And so I want to just briefly, I don't want to discuss all this physics in general, but I just wanted to say for many years, we and others used optical techniques to detect the domain walls. This is so-called magneto-optic Kerr microscopy, where you reflect a polarized plane of light from the surface of a magnetic film, and the plane of the polarization of light is rotated by the direction of the magnetic moment in the racetrack. So in the upper racetrack, this is 3.0. On the right-hand side, you can see the structure in a cartoon form. The structure of that racetrack consists of a cobalt, nickel, cobalt sandwich, where the cobalt layers are roughly 1.5 angstroms thick, and the nickel layers 7 angstroms thick. So the magnetic layer thickness in this racetrack is 1 nanometer. And the platinum layer underneath, which is used to provide the spin orbitorks, is just 2 or 3 nanometers thick. So the racetracks here are very, very thin. And down below, you can see this synthetic anti-ferromagnetic racetrack. You can see a series of domain walls moving backwards and forwards by current pulses that are applied in the positive and then the opposite direction. And these domain walls move at speeds of more than 1 kilometer per second. And in the bottom right, you can see a cartoon of the structure. It consists of the same cobalt, nickel, cobalt layer in the top, but there's a second cobalt, nickel, cobalt layer separated from the first one by the yellow layer formed from ruthenium. And in 1990, I demonstrated for the very first time that through nearly all the transition metals and the noble metals like gold and silver, then all these metals become spin polarized when they are placed adjacent to a magnetic film, and the spin polarization is oscillatory, and this leads to an oscillatory magnetic coupling. Let's say through ruthenium is a very special case. When ruthenium is very, very thin, the coupling is anti-ferromagnetic. When you increase the ruthenium thickness, the coupling between two successive magnetic layers sandwiched by ruthenium becomes ferromagnetic, and then becomes anti-ferromagnetic again with thicker ruthenium, with a period of approximately 10 angstroms. This is something I demonstrated in 1990, 1991, and this is true for nearly all transition metals and noble metals. This enables us to build very interesting synthetic anti-ferromagnetic structures such as this one. And then essentially the motion of the domain walls by current pulses derives from the spin Hall effect in these proximity layers. And I haven't discussed this, but it turns out very importantly is that the domain walls themselves have a chiral structure due to a so-called interface Dzyaloshinskii-Murray exchange interaction. I'll come back to this a little bit later. But this chirality is something we first demonstrated, and it's critically important to the motion of the domain walls in a synthetic anti-ferromagnetic racetrack, and in the racetracks 3.0, it means that all the domain walls now move in the same direction under current, but only because the domain walls have the same chirality. If they had the opposite chirality, they would move in the opposite direction. So now, I apologize, I'm unfortunately suffering from a cold. In my institute over the last 6 years, I mentioned we built this system, which is a series of thin film deposition systems connected by an ultra vacuum tube. And on the left-hand side, I don't know if you can see this, but in this, okay, no, that one now. Let me see now. Previous, anyway, pointer options. Oh, here, well, let's make it laser pointer. Yeah, in this tube, can you see this? This orange tube is 15 meters long. It's an ultra high vacuum tube. And we have built little robots that will pick up a substrate on which we deposit these ultra thin heterostructures and insert the substrate into one of these deposition systems. Let's say this is Mango. Mango is a homemade system which we designed to have up to 44 different sources of materials, either a magnetron sputtering source, an ion beam sputtering source, or an effusion cell, like as in a molecular beam epitaxy. We can have 44 different sources, so we can make structures from a wide variety of different materials, and each of the layers that we form can be atomically thin. In this way, we can make complex structures. We can also combine this Mango system, let's say, with a pulsed laser deposition system using energetic beams of light, or with a molecular beam epitaxy system. We have two systems connected to this tube. One is designed for oxides, one for nitrides, and we can automatically switch a substrate between one of these systems to combine complex heterostructures formed from these very different thin film techniques in this way. So if I just go back to the then basic ingredients for racetrack memory, I mentioned already perpendicular magnetic anisotropy. If you take very thin magnetic layers formed, let's say, from cobalt and nickel, the interfaces break symmetry and give rise to an interfacial anisotropy, and this can be increased by using layers like platinum with strong spin-orbit coupling. And this interfacial anisotropy is critically important to creating tiny, tiny magnetic domain walls. The very large anisotropy means the moments in the racetrack want to point up or down, as shown by these blue and red regions, and the domain walls in between are just a few nanometers wide. At the same time, these domain walls are either clockwise or anti-clockwise. They're chiral domain walls due to an interface exchange interaction between this underlayer, let's say platinum, and the first cobalt layer. This interface breaks symmetry and leads to a very, very interesting so-called Dielerzinski-Maria interaction, which means that the cobalt atoms are exchange coupled via the platinum in the neighboring layer. Because the platinum's on one side, this breaks inversion symmetry and leads to a very interesting chiral interaction, which was first proposed many, many years ago for spin glass systems. This interaction leads to the moments pointing in a chiral direction. So let's say if we go to this racetrack where you have a red moment pointing up and the blue moment pointing down, this interface Dielerzinski-Maria interaction causes or stabilizes a domain wall, which is nail-like. The magnetization will rotate from up to down in the plane perpendicular to the wall. This is a nail wall. At the same time, it will rotate in a clockwise interaction, let's say for platinum, but an anti-clockwise for tungsten. And this means that when you go from up to down, then in the middle of the domain wall, shown by the green arrow, on the left, it points to the right. And when you go from down the blue direction to the up red direction, that green arrow points to the left. And this is a chiral. So the chirality of these walls is formed by this interface Dielerzinski-Maria interaction. So the interface with platinum does two things. It creates anisotropy. It creates this very interesting exchange interaction. At the same time, there's a proximity-induced magnetization in the platinum. The platinum becomes slightly magnetic. It turns out that's very, very important. It can be giant. The neighboring platinum moments have a magnetic moment of about 1 Bohr magneton. And the platinum layer also gives rise to the spin Hall effect, converting charge current to a chiral spin current. So we've recently found some materials that have even greater charge to spin current conversion ratios. These are formed, for example, from iridium and aluminum, or iridium and gallium, which we think are very, very interesting compounds because at room temperature, these compounds, iridium, aluminum, form atomically ordered species, enabling us to create very interesting heterostructures by epitaxy. And then finally, the basic ingredient for a racetrack, which is critically important, you need a racetrack with zero net magnetization. So you get near zero dipole fields. And we call this a synthetic antiferromagnet. This is the most important ingredient for racetrack. In fact, all of these ingredients are super important. Together, the anisotropy, the chiral interaction through the Dzerzhinsky-Maria interaction, the proximity-induced magnetization, the spin Hall effect, and the synthetic antiferromagnet creates racetracks that have extremely interesting properties, where the domain walls can be moved at speeds exceeding 1 kilometer per second at current densities that don't significantly heat the racetrack. This is what makes it super important. Now, I mentioned before, we use optical means to detect the motion of domain walls. We basically apply current pulses, the domain walls move, we take a snapshot of the domain walls, we apply more current pulses, they move, we take another optical snapshot, and we look at the motion of the domain walls. An alternative technique is to use this anomalous Hall sensor device, as I mentioned earlier. And this is some very recent work we've done here, where we've used anomalous Hall sensors to explore the motion of domain walls in racetracks that are as narrow as 50 nanometers. So before, using optical Kerr techniques, the racetracks were 1 or 2 microns wide. Now we can look at racetracks only 50 nanometers wide, and we locally read the magnetization using a Hall sensor. So this is some work in particular that was led here by Jae-Chun Jeon, a group leader in my department. And what we did was we built a racetrack shown on the left in this cartoon. This cartoon is to size. So the blue and red regions correspond to a cobalt, nickel, cobalt racetrack magnetized vertically. And the yellow region is the platinum underlayer. So the platinum underlayer here is 5 nanometers thick, and the racetrack is approximately 1.5 nanometers thick. And on the edges, these yellow regions are electrodes, which we designed by electron beam lithography so we can measure locally the transverse Hall voltage. And in the devices I want to briefly show you, we have 16 of these Hall sensors designed from the platinum underlayer. And a very important point is, in this cartoon, you may notice that the width of the magnetic racetrack is narrower than the width of this platinum underlayer. And this is by design. So it turns out what we discovered, as shown in the next foil I'm going to mention, is go back. Depending upon the ratio of the width of the magnetic layer compared to the platinum layer, if we make the platinum wider, the Hall voltage will detect the magnetization from a further distance from the Hall electrodes. And this is very important because it enables us to detect one domain wall anywhere along the racetrack by proper design of the width of the extension of the platinum electrode. And this is what we did here. This is a paper we published just at the end of last year in Science. And in this paper, we demonstrated that we could follow the motion of one domain wall as it's moved by current pulses from one end to the other of a racetrack. And in this case, you can see that the current pulse is shown at the bottom. They're either in the negative direction, the domain wall moves from the left to right, or the positive direction, the domain wall moves from the right to the left. And as we increase the intensity of these current pulses, the number of pulses needed to move the domain wall from the left to the right or right to left shrinks. And in this way, we could demonstrate that we could resolve the position of a domain wall to a few tens of nanometers and follow it continuously as it moves from one end to the other. And we could also demonstrate that we could position domain walls with great accuracy to the inaccuracy of a few tens of nanometers. Here are 4 distinct positions of a domain wall along this racetrack. And we could position two domain walls so that they're only 100 nanometers apart. These dimensions are basically the dimensions that are needed to make a technologically relevant racetrack. So we think today we've come to the point since we started 20 years ago that we can now build a racetrack that is technologically relevant and has shows great promise. So we're very fortunate that Samsung Electronics in Seoul has supported our work here for the last 6 years to demonstrate this possibility, scaling a racetrack to dimensions that are technologically relevant. And recently, we've also demonstrated we can integrate a tunnel junction device into a racetrack. And as shown on the right-hand side, here is a schematic cartoon of a 100 nanometer long racetrack with two electrodes to left and right. And there's three tunnel junctions. The only one in the middle is of interest. And as the domain is moved from the left to the right by a current pulse, which is only 500 picoseconds long, we can detect the position by the state of this tunnel junction, the resistive state, which varies from a high to a low value. And in this way, we've demonstrated we could build a racetrack with a single domain wall, moving it a few hundred picoseconds from one end to the other, demonstrating a very dense and very, very fast non-volatile memory that could, in principle, compete with the fastest memory today, which is a static random access memory in a smaller form factor and with non-volatility. So we think this is also a very exciting development. So demonstration, fully functional racetrack for the first time, ultra fast and low energy writing is possible. Okay, now I want to just make a few more comments. I think I'm probably running out of time. I mentioned earlier on that we're very interested in three-dimensional technologies. And here I wanted to mention a very interesting project by one of my PhD students, Kei Gu. And what he demonstrated was that we could build a racetrack in the form of a very thin membrane. So to do this, we grow a racetrack on a single crystal substrate formed from strontium titanate. On this substrate, we first grow using pulsed laser deposition this strontium-3 aluminum-206. This is an oxide material which is water soluble. On top of this oxide material, we grow first a buffer layer of tantalum nitride, and then on top of that, we go the racetrack, a platinum layer, the spin orbit layer, cobalt, nickel, cobalt, and magnesium oxide. What you do then is this is on a 5 by 5 millimeter squared substrate. So what Kei Gu does, he dissolves this membrane after we've grown the racetrack in water. And then in water, he transfers this ultra-thin membrane, which is now consisting of just the tantalum nitride, platinum, cobalt, nickel, cobalt, MgO. He transfers this onto another substrate. In this case, as shown in the top right, he has formed in sapphire these little hillocks. These are up to 1 micron tall. And basically, he moves the racetrack on top of these hillocks. And as shown in the bottom left, this is a cross-section transmission electron micrograph of this membrane, the 3D racetrack. And in cross-section, you can just see it looks like this black line, which follows very closely the underlying sapphire substrate. And so we've demonstrated the possibility then of building essentially a three-dimensional racetrack. And in this racetrack, then we demonstrated that on the right-hand side, this SAF is a synthetic anti-ferromagnetic racetrack. And what Kei Gu showed was that the velocity versus current profile of the domain walls is the same in the original film deposited on the strontium-3 aluminum-206 as it is now in the membrane without that oxide layer, which is folded onto this hillock in the substrate. So if you like, it's the first three-dimensional racetrack. We've also, this is another project of a PhD student, Andre Farina. He demonstrated the possibility of building using something called multiphoton lithography. This is basically, we have a very, very tiny beam of light, which is very, very intense. And we use that to photopolymerize a liquid polymer so that it forms a solid object. And this enables us to build scaffolds, as shown in the bottom cartoons, of almost any shape with a voxel size. The smallest size possible is 50 nanometers. And so these 50 nanometer voxel sizes is several times smaller than any commercially available printing device. And then here we've used this to grow magnetic ribbons. And this is a results from a paper we published early this year in Nature, where we demonstrated for the first time a truly three-dimensional racetrack. And in this picture on the left, bottom left, you can see essentially like a bridge we formed from the racetrack with a twist, a geometrical twist. And on the top of this geometrical surface, we build a racetrack which has this chirality introduced, as I already mentioned, by this Dzerzhinsky mirror exchange interaction. And what we demonstrated was that the motion of the chiral domain walls is influenced by the chiral surface on which they are deposited, and that whether the chirality of this surface has a torsion to the left or to the right strongly influences the motion of the domain walls. So this is the first demonstration of the interaction of a geometrical and a spin chirality. So now, maybe in just the last 3 or 4 minutes, I wanted to mention that we also working heavily on not on chiral domain walls, but more complex chiral spin textures. And you probably are familiar with these, that some time ago it was proposed and then first found by Christian Fleidrer at the Technical University in Munich. He found a so-called block skyrmion in a chiral material, manganese silicon. So what does that mean? It means that in some materials, some magnetic materials, which are ferromagnetic, typically with strong out-of-plane magnetic anisotropy, instead of forming a uniform magnetized ground state, they form a state in which there is an array of skyrmionic objects. The skyrmionic object, for example, in the left-hand side, this block skyrmion, is magnetized on the outside, let's say in the positive direction, but inside it's magnetized in the opposite direction. And this domain wall, which is circular, is a chiral wall. In this case, this block wall here, you can see the magnetization rotates from an up direction on the outside to a down direction on the inside, and it rotates in a plane which is parallel to the tangent to this object. And this, all the way around the object, the magnetization rotates in the same way. So on the right-hand side, you see the magnetization in the middle of the domain wall is pointing up. On the left-hand side is pointing down, because the chirality is the same all around this object, and the chirality is typically introduced by a bulk version of this exchange interaction, this Dzerzhinsky mirror exchange. So it's typically found in systems with a lot of spin-off coupling. On the right-hand side, you can see a nail skyrmion, same as the block, but here the magnetization rotates from up on the outside to down on the inside by rotating along the domain wall, just like the domain walls in the racetrack I mentioned earlier. And now in this case, in both the block and nail cases, the domain wall has the same structure all the way around the object. However, it was theoretically predicted that in certain materials with a lower symmetry, then depending upon the crystallographic direction, the sign of this Dzerzhinsky-Maria exchange would change sign. So in some directions, you would get a nail wall, shown in this, let's say 3, and in some directions, you get a block wall. So and this forms something called an antiskyrmion. Antiskyrmion was predicted theoretically, but never observed. And we were the first to observe this shortly after I came here to Germany. And we did this using Lorentz transmission electron microscopy. In this case, we take a single crystal material. We cut out of the single crystal a very thin layer, which is electron transparent, using focused ion beam milling. And we pass a high energy electron beam through this thin membrane. And the electrons are deflected through Lorentz forces induced by the component of the magnetization in the plane of this lamella. And then you can calculate what you expect to see. And it turns out that for the block skyrmion, you expect to see an intense beam of electrons because they're deflected to either the inside or the outside of this object. So you basically see this simple spot of high electron intensity. Whereas for a nail skyrmion, the electrons beam are deflected by the in-plane components of magnetization circumferentially. So basically you see nothing unless you tilt the sample. On the other hand, in an anti-skyrmion, we calculated that we would see this very interesting clover leaf shape-like object with two white regions of increased electron intensity and two black regions of decreased intensity. And actually, that's what we observe. If you look on the bottom top left in A, you can see what is the first anti-skyrmion that was observed by ourselves at room temperature in a Heusler compound, manganese actually 1.4 platinum silicon. This is very interesting material. The Heusler family actually has a lot of materials. And what we demonstrated was these antiskyrmions are formed in arrays, hexagonal arrays. And by applying magnetic field in the microscope, we could eventually cause these antiskyrmions to disappear at high enough magnetic fields when they form a uniform magnetic state. So these in the intervening time, we've used different techniques to explore these objects. We can use magnetic force microscopy, in which we detect the outer plane component of the stray field above the surface. We could use this to detect the skyrmions and antiskyrmions. And it turns out these antiskyrmions, before they're formed, the magnetic spin texture is actually a helical texture where the magnetization rotates from up to down in this one-dimensional fashion. And the magnetic force microscope, if you look in E, this is the component of magnetization. It rotates from up to down as you move along this slab, this lamella. And what we discovered was that the period of this helical magnetic phase increases uniformly with the thickness T of the lamella in which we image this one-dimensional helical object in this manganese platinum tin structure. So it turns out if we change the magnetic field, we can switch this helical structure shown in A to a series of these magnetic dots. These actually are antiskyrmions as imaged in the magnetic force microscopy. So totally different from Lorentz. Lorentz measures the in-plane components of magnetization. Here we're measuring the outer plane stray field, and they look like simple objects. And again, we found that the diameter of these antiskyrmions increases with the thickness of the lamella in which they're imaged. And the reason for this is because of the role of the dipole-dipole fields. We demonstrated a very, very important and in thin layers suppress the size of these objects, which otherwise are much larger. So for thicker lamella, these objects become microns in size, and we can detect them optically. Okay, now I think I'm going to come to an end. It turns out we've also discovered in the same material, we discovered another type of spin texture, which we called an elliptical block skyrmion. And the reason why skyrmions have attracted so much interest is because they're supposedly topological, which means because of their structure, they cannot be converted into a uniform state very easily, and therefore they're so-called topologically protected and will be stable against perturbations. And this was the first time in this paper where it had been observed that the same material could display two distinct topological spin textures, and we proposed we could use these to create an advanced racetrack where we could store information in the form of these spin textures, whether antiskyrmions or whether elliptical block skyrmions. I think now I'm going to, since I think I'm running out of time, so I was going to talk about chiral antiferromagnets, which are very, very interesting, which we see in these Kagome systems like manganese-free tin. And I was going to talk briefly about how we could use these chiral structures to create spin triplet supercurrents by proximity to supercurrents. This is one of our most important projects. We want to create a new form of unconventional superconductivity in which the Cooper pairs have their spins parallel to one another, and these spin triplet supercurrents should enable the the manipulation of spin textures at ultra low temperatures using dissipationless currents. This is something we're working on. I'm going to skip the next part and just come to my conclusion. Okay, by the way, we want to use this spin triplet supercurrents and another effect that we discovered, a Joseon diode effect, as a reading device to build a new form of racetrack memory that would operate at cryogenic temperatures. I think this is super exciting. And so let me come to the end. And I wanted to then my talk to briefly discuss spintronics, the concept that we could use the electron spin with and the new physics related to that, in particular currents of spin polarized electrons. On the one hand, we demonstrated several years ago we could build a sensing device with a sandwich of two magnetic layers separated by a copper layer. This gives rise to a spin valve sensor that is the most sensitive detector of tiny magnetic fields that is known today. This enabled a massive increase in the storage capacity of magnetic disk drives, making possible access to all information today. The magnetic tunnel junction we first proposed in 1995, could be used to form a very interesting high-performance, non-volatile magnetic random access memory. We demonstrated that many years ago, but it became only in 2019 a foundry technology using materials that we first proposed in a paper in Nature Materials in 2004. And this is already replacing several forms of conventional charge-based memories. And finally, I think racetrack memory is really a very interesting technology that is basically becoming to fruition today. It could replace magnetic disk drives. Most likely, they will find other applications before that. But the concept is you actually move the data itself. Unlike any other type of data device, the data itself is moved by spin currents, moving to reading and writing devices, and promises a non-volatile, high-performance, low-energy, small form factor, highly reliable, massive data storage device. And already there's startup companies for racetrack memory. And I think this is a very exciting technology that is emerging today. And so therefore, I would argue that we have created three successful spintronic technologies, all based on spin currents crossing atomically engineered interfaces, many more to come. So I'd like to thank you for your attention.
Thank you so much, Professor Parkin, for the very interesting talk. This is now open for questions and comments. I must say that we are here in the audience mostly working on fundamental research, and it is very inspiring for us that this can meet, and in your case, it's always the case that you deal with applications, with industrial applications.
Yes, I think applications, to me, I think the intersection of fundamental science and applications is really exciting. I'm happy to answer any questions if there are any.
Yes, Yuri Georgich, Naiduk, please.
Okay, thank you. Thank you, Professor Parkin, for your fundamental and comprehensive review of magnetic type racetrack memory. My question is maybe simple from one side. As I understand, magnetic type of memory has some restriction to the size of domain due to domain walls and superparamagnetic effect. What is your opinion? Is now magnetic type of memory reached the limit or not yet? And the second part of my question, what is advantage and disadvantage of magnetic type of memory in comparison with resistive type of memory? And what is the future for memory? Thank you very much.
Yeah, thank you very much for your question. So the, of course, advantage of magnetic, as you say, of course, if you shrink the magnetic entity to a tiny device, then superparamagnetism will overcome the orientation of the magnetic moment. So this is a problem with magnetic disk drives, that in order to decrease the size of the magnetic bits, you need to increase the magnetic anisotropy. That will make the magnetic bits more stable in smaller areas, but then it becomes more difficult to write. So basically, you've reached the end of the roadmap. It's not possible to have writing fields that can write the magnetic regions with very, very high magnetic anisotropy, so that restricts the size, just as you said, because of superparamagnetism. So there are many ways around it. For example, as I said at the end, we're super interested in cryogenic technologies like racetrack. And then, of course, we go to cryogenic temperatures, then we're no longer confined by these, the superparamagnetic effect at low temperatures is several hundred times less important. So this is a very exciting possible development. And cryogenic magnetic memory technologies could be very important, e.g. for quantum computing. So quantum computing needs memory operating at the same temperature. So I think racetrack memory as a cryogenic memory using these new phenomena we've discovered in the last few years is a very exciting possibility. Back to your question though, on the other hand, like racetrack memory, because it's vertical, just like VNAND, NAND flash, that works by no longer shrinking laterally, where you no longer have enough electrons in a capacitor, but by going vertical, then you can have larger devices that have more electrons that can overcome the limitations of those small devices. So this is similarly with racetrack memory, we can make since it's in the third dimension, we have a lot more space, so we can overcome the super paramagnetic limit. The second question, so I think magnetic materials have enormous advantages in terms of scaling. The second question about resistive random access memories, then these resistive random access memories typically involve destruction. You have to move atoms around, typically oxygen atoms, and typically motion of atoms leads to wear out. So the big problem with resistive random access memory is that the devices cannot sustain multiple writing events without their destruction. Typically, also most resistive random access memories involve forming paths which are atomic in nature, and this leads to, again, problems of reproducibility. So I think resistive random access memory, very interesting, but it's been around for decades, not yet, I think, super important, but of course, potentially very exciting as well. But it has maybe different applications, maybe applications where you don't need to write so many times.
Thank you very much.
Alexander Borisenko, please.
Very much for your amazing talk. I'm sorry, for some strange reason I can't turn on my camera, so I beg your pardon. My question is related to the analogy with the situation in polycrystalline solids. When there is effect called Lifshitz-Lyozov coalescence, when big crystallites tend to incorporate small crystallites with time, and the mean size of the crystallite grows with time. Is there an analogous effect when, let's say, you have some adjacent bits of the same sign, and one bit of the opposite sign between them? Don't the big domains want to incorporate small domains? Or in other words, what is not there an issue with stability in time in this racetrack?
Well, thank you for the question. Very interesting question. And I would say one point I mentioned, these chiral domain walls have an innate stability that it's difficult to evolve them to a non-chiral texture. So it's like these topological spin textures. These are stable because of the topological characteristic, and it's very similar to these chiral domain walls that I mentioned. So this is a very interesting question. How do we ensure that the domain walls have sufficient stability, typically technologically for memory applications? They need to be stable over 10 years over some wide range of temperature. And so we think that the domain walls we have are sufficiently stable, or we can create racetrack devices where you have regions where they would be most stabilized, e.g. by modifying either the geometrical shape or the size or the magnetic materials locally. So there's a lot of possibilities to create further stability of the domain walls if needed, but that doesn't appear to be necessary in the structures that I introduced. But it's a very interesting question. Thank you.
Thank you very much.
Yes, Andrei Sotnikov, please.
Thank you, Professor Parkin, for very inspiring talk. My question is about this skyrmionic direction for racetrack memory application. You mentioned that the standard conventional racetrack perhaps less stable to perturbations in comparison with skyrmions. What kind of perturbations are most crucial in this respect, and what perturbations skyrmions can overcome and be more stable for technological
So
applications?
skyrmions, I think it's also, the concept was they should be topologically stable. It's not clear exactly what that means. Of course, if you change the magnetic field or temperature, skyrmions can disappear or they can evolve into other spin textures. So it's not so clear. But nevertheless, understanding the stability of these objects is of course critically important. And how to make sure that they're stable over perturbations. And the perturbations I meant was, e.g., temperature excursions. And as I said, typically, depending upon whether the technology is for military or consumer applications, then the range of temperature of which you would specify stability is distinct, but nevertheless, it's pretty high, maybe at least 100 degrees centigrade, minus 30 degrees centigrade. So it's a very enormous range of which you have to create stability. Other perturbations are magnetic fields. So then you can of course shield devices against magnetic fields, but that can be expensive, not that expensive. Alternatively, let's say the synthetic antiferromagnet, where there's no net magnetization, is already very robust to external magnetic fields. So this is a huge advantage. So skyrmionic textures have major problems in that regard compared to a synthetic antiferromagnetic racetrack. So I think this concept of synthetic antiferromagnets is super interesting. This is why in the last part of my talk I didn't discuss, we're very interested in all types of antiferromagnets, particularly chiral antiferromagnets. So chiral antiferromagnets were predicted and then later discovered, including by ourselves. We were one of the first to demonstrate that they can show properties analogous to a ferromagnet. So let's say a chiral Kagome antiferromagnet like manganese 310 actually exhibits an anomalous Hall signal, even though there's no net magnetization. That's because of the topological nature of these materials. This is very, very interesting. So that means you have no net magnetization innately, but yet they look like a magnet. Therefore, they're impervious, even more impervious to stray fields. This is very important. Moreover, it turns out that these antiferromagnets could be used even to make interesting tunneling junctions. So recently, we have a paper published in Nature recently where we demonstrated we could take a two-dimensional antiferromagnet, which is actually chromium sulfur bromine. One layer is ferromagnet in one direction, in plane, but it has some in-plane anisotropy. It's very unusual, it's orthorhombic. And the second layer is antiparallel to the first one. And then we demonstrated now, you take this bilayer and the second bilayer, which you twist at an angle, and then you can orient the magnetic moments of these two bilayers to be essentially parallel, antiparallel, and create a tunneling junction. These are semiconducting layers. Tunneling by just simply tunneling through this two bilayers with no moment, you can see giant tunneling magnetic resistance values exceeding 1000%, which is very, very interesting. So this approach to new forms of tunneling junctions involving these two-dimensional materials, which are semiconducting or insulating, which are magnetic, is very, very interesting, and I think would be impermeable to external magnetic fields. So this is another different approach that, of course, is just emerging from these new 2D materials. Very interesting question. Thank you.
If I may, one additional question that appeared during your answer. What do you think about alter magnets, which have high stability usually compared to regular magnets?
Alter magnets don't have high stability compared to regular magnets. And alter magnets, as you know, simply are very interesting. They have been around many, many years, but now people have given them a new name. Alter magnets are where you have no net polarization integrated over reciprocal space. But in some regions of reciprocal space, the bands are spin polarized. aggregate nothing. So it's like valleytronics, which is a 2D concept where you have different values which are polarized in different ways depending as you excite the systems with light, for example. One direction it's polarized up, one direction is polarized down. Very similar. So this concept, if you like, of momentum controlled spin polarization, it's really, I feel like it's an old concept that has attracted new interest in the form of altermagnets. And it's very interesting. However, altermagnets, I don't think they're more stable, but they have very interesting properties akin to chiral antiferromagnets. These Kagami systems, I think, are even more interesting because they're innately stabilized by these chirality. They also we showed in 2017, display anomalous Hall signals, anomalous Nernst signals, very exciting, very interesting. So I think, generally speaking, anti-ferromagnetic spintronics, very interesting. The first application of anti-ferromagnetic spintronics is the synthetic antiferromagnet. People generally overlook this, but this has been used since 2007. The very first spin valve was not stable without using the synthetic antiferromagnet, which was my invention and my proposal to enable devices with no long-range dipole fields. It's been used since 2007. Altermagnets has just appeared in the last 3 or 4 years. The chiral antiferromagnet dates from about 2015. All of these follow synthetic antiferromagnets. Synthetic antiferromagnets already have many of the properties that are claimed for altermagnets and chiral antiferromagnet, in my mind, my own personal opinion. I would say synthetic antiferromagnets are even more exciting. And in fact, this chromium sulfur bromine work we just published in Nature is also very interesting because you have 2 layers, ferromagnetic layers, separated, coupled antiferromagnetically. A ferromagnetic layer you can then use for scattering, for detection, and it makes it even more interesting, even so, than maybe some of these altermagnets. Now, altermagnets is super interesting, but I think it's just another facet of the field of antiferromagnetic spintronics, which I believe started 20 years ago with the synthetic antiferromagnet. But very, very interesting.
Thank you.
Next question from Valentin Volobuev.
Thank you, Professor Parkin, for this interesting and historical talk. My question is as well about history. Like I somehow missed this point about magnesium oxide, which is used in all this tunnel junction. Why it is this magnesium oxide? What's special in this material? Thank you very much for the
Okay, so conventionally,
simple
concept of a magnetic tunneling junction dates back to the 1980s. So it's a very old concept by Julia, demonstrated already in 1980s at low temperatures, but not at high temperatures. So for all these years, people have searched for tunneling junctions that could enable magnetic tunneling junctions at high temperatures. It turns out very, very difficult to create a tunnel barrier which is sufficiently thin that you can get current without the tunnel barrier having essentially holes and allowing conventional current to flow using in defects. So it turns out that there are only 3 tunneling barriers that have largely been used, largely for superconducting Josephson junctions. And these were aluminum oxide, aluminum nitride, and magnesium oxide. Magnesium oxide, it turns out, is very, very interesting because it's nearly impossible to create defects, oxygen vacancies. Nearly all oxides form vacancies. Vacancies typically have spins, which are very bad for tunneling and also allow for indirect tunneling. So in magnesium oxide, it turns out it's one of a family of insulating materials that were predicted to allow for spin polarization. In other words, even though it's non-magnetic, if you couple that tunnel barrier to a magnetic layer in which let's say the electrons in states polarized in the up direction, let's say if they have sp character, then those are very extended states, and so they can cross a tunnel barrier and insulate. They will extend into the tunnel barrier. Basically, it depends on the the imaginary component of the wave functions in that material. If they extend a long way, then the electrons can pass a tunnel barrier. If, on the other hand, the opposite magnetization of the states at the Fermi energy have a very distinct electronic character, let's say they're D-like, they're highly localized, the extension of their wave functions into the tunnel barrier is limited. This leads to an innate differentiation of the tunneling. So let's say the extended states of one spin can pass the tunnel barrier, the tunneling probability is higher than the localized states of the opposite spin, then they cannot. This leads to a spin filtering in a tunnel barrier, even though it's non-magnetic. This is what all tunnel barriers can do if you couple them to the right magnetic material. And it turns out that MgO is a very simple cubic system. If you couple it to body-centered cubic, cobalt or cobalt ion or iron, and it turns out all those magnetic materials have this characteristic that the spin up and spin down electronic states have this very distinctive electronic symmetry that enable this spin filtering. And so we were the first to demonstrate that we could spin filter through magnesium oxide. And it turns out, it's, nowadays, even though dating back in history, 1995, we proposed using tunnel junctions, and everyone said it's impossible. How could you make an ultra-thin oxide layer uniformly across a 300 millimeter wafer substrate that you would need to build CMOS devices? And in fact, that's what we demonstrated. And today it's used. You can build on 300 millimeter wafers, a 1 nanometer thick magnesium oxide layer, even though the tunneling current depends exponentially on thickness, it's basically uniform across the whole wafer. So it is remarkable that it works at all, but it does work. And we were the first to demonstrate this. And it turns out I had some tricks to enable us to build a 1 nanometer thick magnesium oxide layer that was essentially pinhole free and could enable tunneling and demonstrate this thin polarization and giant tunneling magnetic resistance at room temperature and even larger effects at lower temperatures. So we did that in 2000.
Thank you very much.
Turns out IBM at the time didn't want me to publish. They thought it was so important. We're not allowed to publish. Eventually, took several years. Then we could eventually publish them in this paper in Nature Materials in 2004.
And if it is allowed, one small question. It's about you show this nano devices with magnetic wall propagating through. So my question is because I noticed that the distance between I think that this domain walls was a little bit different. So how this affect devices? Because probably its domain size is a bit different. So how
It depends.
can you comment on this?
Optical images I showed using Kerr microscopy, then you're right, the racetracks are microns wide, and the domain wall is actually microns apart because of the limited spatial resolution of Kerr microscopy, which is roughly 3/4 of a micron. Later on, recently we've demonstrated using these anomalous Hall signals, then we can demonstrate we can position domain walls 100 nanometers apart without them disappearing. This is an earlier question. They're stable and can be moved together backwards and forwards. So in those cases, though, we cannot resolve microscopically those walls. We just infer from Hall measurements that the domain walls, the spacing, and that they survive motion backwards and forwards. That's the idea. I don't know if that answers your question.
Thank you very much for your answers. Thank you.
Let me ask about multi-photon lithography.
Oh, yeah. Okay.
Was it really multi or few photon lithography, and how many photons did you use, and why was it important to use several photons instead of one?
Okay, it's multi-photons. I don't know how many photons there are, but it's multi-photons. And the idea is that a single photon, you have to pass the beam through this liquid polymer. The liquid polymer is designed to have a component that will react with, will be excited by photons. So if you have too many photons, then the path of photons through the liquid polymer to the region of interest, then it'll convert that polymer into solid polymer. So you need a beam where at the end of the beam, you have a highly focused optical beam with a lot of photons in this very small voxel, which is why we're using a super resolution technique to enable the end of this optical beam where we focus it to be 50 nanometers in size, where you have enough photons to cause polymerization, whereas the rest of the beam will not polymerize the liquid polymer through which it is passing. This is why we know it's a multi-photon process. If it were single photon, then all the polymer would be converted to the solid and it would not work. We need multi-photons to enable us to have the tiny super resolution beam to convert the liquid to a solid just at that point. That's why it works. In fact, it's even cleverer than that. So my student, Andre Farina, he was very clever. He built this device, and he also noticed that during this process, you emit light. So he actually uses the light to microscopically image the polymerization process. So we're building this solid device. You move this photon beam backwards and forwards. So you just polymerize where the beam is passed, and then he can detect the polymerization, and then he can actually correct on the fly if the process was not perfect. And this enables us to build more perfect devices than would otherwise be possible. So it's a very, 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 I think it's quite a very clever technique, actually. But it took several years. This project took quite a few years before we got our first result. But that was like one PhD project.
Thank you. Yes, please. One or two short questions we can ask.
Okay.
Please.
Oh, he's silent.
We do not hear you.
Is the tennis microscope on?
May I ask?
Yes.
Thank you very much, Professor, for your very interesting report and amazingly picturesque presentation. I just wanted to ask, can you comment something on triplet superconductivity? Are there clear evidence on this?
Okay, that's a super interesting question. And the concept of triplet superconductivity, as you know, has been around a very long time. And the concept of finding a triplet superconductor in bulk materials, there are very, very few. And strontium ruthenate was one that was proposed to be a triplet superconductor for 20 years. And then recently it was decided the measurements from 20 years were incorrect, and it's not a triplet superconductor. The same scientists who proposed it was, after 20 years, they said, oh, it's not. Other possibilities are uranium ditelluride is one of the recent materials that it's also argued it is a triplet superconductor, but there are very, very few in bulk materials. However, it was also proposed maybe 15 years ago or 20 years ago that you could create a triplet superconductor by proximatizing a magnetic material with a conventional S-wave superconductor. And then if you have an S-wave superconductor in proximity to a very, very thin ferromagnetic layer, you will create a triplet component because the ferromagnet favors the spins that are parallel, and it forms a small triplet component. And then Sebastian Bergeret 20 years ago proposed, well, if you take proximity, S-wave superconductor, proximity to a ferromagnet, and then you have another ferromagnetic layer, which is orthogonal to that first layer. The first layer has to be sufficiently thin that you don't destroy all the superconductivity. Then you will create a triplet pairing supercurrent that can flow over long distances. And this has been a subject of research by a number of groups, e.g. Jan Arts in Leiden, other groups around the world, in Cambridge and Michigan and Minnesota. These groups have, demonstrated, okay, they have long-range proximity-induced supercurrents that flow through non-linear magnetization. So typically they would create a structure, let's say conventional ferromagnets like nickel, cobalt, and you'd have them oriented in different ways. One can be perpendicularly magnetized, one can be in plane. So we've also done this, and what you find is then some evidence that the proximity-induced supercurrents will flow over longer distances through magnetic materials in which you have magnetic layers with orthogonal magnetization. So what we demonstrated was, okay, if you can do that in multi-layers, or in, let's say, the work by the Cambridge group in holmium, which has an innate helical structure at low temperatures, they claimed on holmium you could induce long-range superconductivity. Very interesting. But you could also do it then in this chiral antiferromagnet with lots of moment on manganese, but all the manganese atoms have their moments at 120 degrees to each other, non-collinear. We demonstrated, we believe, long-range supercurrents flowing through manganese-free tin, even though you've got lots of magnetization that should spin depolarize or kill the superconductivity. Now what we've demonstrated recently is that you can go beyond this, and you can imagine, let's say, topological materials which have spin polarized surface states. And in these surface states, we've also demonstrated long-range proximity-induced supercurrents from, let's say, niobium on top of nickel ditelluride, which has a surface state which is spin polarized. The net material is not magnetic. We demonstrated supercurrents flowing over distances of up to 1 micron, very long distances. You create a Josephson junction laterally, long distance, or we can take tungsten ditelluride, where you have a Rashba effect, spin polarized states, and then you can generate vertical tunnel junctions where spin current, proximity-induced supercurrents can flow over long distances. This is the idea. That's the only evidence. However, we believe that if it's true, you can create a triplet supercurrent in this way. In principle, you should be able to use the angular momentum carried by those triplet Cooper pairs to manipulate magnetization. This is what we're trying to do. And I think that would be a direct evidence, more direct evidence for triplet pairing supercurrents. That's what we're currently working on. It's never been demonstrated to date, as far as I know. That's what our goal is. Hopefully we'll succeed in the next few years. But anyway,
So
thank you.
by now you have only superconductors with induced triplet superconductivity
Yeah, that's
by
true.
spin
However,
current only.
there are other materials. For example, we're working on europium iron, arsenic, phosphorus, which is supposedly we've grown thin films by molecular beam epitaxy. They have transition temperatures up to 28 degrees Kelvin, and nominally they're supposed to form a ferromagnetic state in addition to the superconducting state. So you'd imagine that system should be super interesting and should have some very unconventional superconductivity. It could be triplet in nature. So I think there are many possibilities for triplet pairing in either ferromagnetic superconductors, of which there are very few, or by proximity of conventional S-wave superconductors with very interesting non-collinear magnetic systems. And I think this is highly promising, or I think actually these topological systems also extremely interesting with these spin polarized surface states or innate spin momentum lock-in in a whole variety of systems. I think these are very interesting possibilities for creating triplet supercurrents. And that's, we're working on all of these, as is our other groups, of course.
Thank you a lot.
Yes, and I also would like to thank you, Professor Parkin, on behalf of our audience. Thanks a lot for this inspiring talk, discussion, Q&A. Very interesting and important was to have you, our guest at our Kharkiv seminar. With this, I probably would like to finish our today's seminar, and all of the attendees are invited to the next seminar in 2 weeks. Thank you very much.
Thank you very much. I very much enjoyed it. Thank you so much. And thank you for the questions. I'll say goodbye.
Bye-bye.
Thank you very much.